In this video, we are going to look at the derivatives of inverse trigonometric functions. So let's start with y equals inverse sine of x, which implies that x is sine y, and y is on the interval minus pi on 2 to pi on 2. Okay, that's the domain for the x equals sine y. And if you remembered from the trig functions, we had something like this. Okay. So made that minus pi on 2 and this pi on 2. That'll be our y, that'll be our x. The reason for doing that was that it made the function 1 to 1 on that interval. Globally, sine is many to 1, it's not 1 to 1, and so you can't have an inverse globally. You can on a restricted domain. In this case, if you remember from those videos, we restricted the domain to minus pi on 2 to pi on 2, and such that the horizontal test could show that it cuts the line once, draw a horizontal line, and that tells you that it's 1 to 1. Okay, x equals sine y, dx dy is cos y, all right, derivative of sine x is cos y, the derivative of sine y, sorry, is cos y. Now, we can take the reciprocal, dx dy is that, so dy dx is 1 over cos y, so long as cos y does not equal 0, okay? But from the identity here, sine squared y, and we'll see that's the case. Sine for this interval here, we'll see that is the case, cos y not equal to 0. Sine squared y plus cos squared y equals 1, or cos squared y equals 1 minus sine squared y. That implies that cos y is plus or minus the square root of 1 minus sine squared y. Okay, but over this interval minus pi on 2 to pi on 2, the actual cos function is actually positive. I mean, it's something going like this. All right, it's going something like so. Cos y, the output of that, is over this interval minus pi on 2 to pi on 2, as you can see, is positive. So cos y is equal to or greater than 0. But just remember the restriction, we don't want cos y equal to 0. So we can't include the point pi on 2, minus pi on 2 and plus pi on 2. All right. Now, so cos y, we take then this, the positive value, square root of 1 minus sine squared y. But dy dx is 1 on cos y. So dy dx is 1 on the square root of 1 minus sine squared y. Now sine y is equal to x, as we saw up here. So sine squared y will be x squared. So we have dy dx is 1 on the square root of 1 minus x squared. And x, as we said, lies in the open interval from minus 1 to 1. Okay, the endpoints are not included. Okay, now, what does that tell us then? Okay, well, in a similar way, we can argue for the derivative of inverse cos x and inverse tan x. But in general, the rule is that if f is a map of the open interval minus a to a into the reals, a is a real number, minus the open interval minus a to a into the reals, where f of x is inverse sine x on a, then f prime of x is 1 over the square root of a squared minus x squared. Now, if a is 1, we get the result that we just derived above. Let's say f is a map of the open interval minus a to a into the reals, where f of x is inverse cos x on a, f prime of x will be minus 1 on the square root of a squared minus x squared. And 3, if f is a map that maps the open interval minus a to a into the reals, where f of x is inverse tan x on a, f prime of x is a on a squared plus x squared. Okay, the derivative there. So what we'll look at now are a few examples of how to use these. Let's start with the first one. F of x is inverse cos x on 2. Okay, then straight application of the rule number 2. F prime of x is minus 1 on 2 squared minus a squared. Minus x squared, sorry. Where the a is, just put the 2 in there. Okay. F of x is inverse sine 2x. Okay. Equals inverse sine x on a half. Okay. So a is a half in this case, then f prime of x is 1 over the square root of a half squared minus x squared, which is 1 on 4 minus x squared. Bit of algebra, you could tidy it all up. 1 over square root of 1 minus 4x squared over 4, common denominator, Same thing here, so we end up with 2 over the square root of 1 minus 4x squared. Okay, that's f prime of x. Let's have a look now. F of x is inverse tan x on 3, then f prime of x is 3, remember a, over a squared plus x squared, so 3 squared plus x squared. All right, let's have a look at some more examples. Y equals inverse sine of x to the power of 5 plus 3x. What we're going to do here, make a substitution, let u equals x to the power of 5 plus 3x, then y equals inverse sine of u, and here we'll apply the chain rule. So dy dx is dy du times du dx. All right. So dy du is the derivative of this. A is 1 in this case, so we're going to have 1 over the square root of 1 minus u squared, times du dx is 5x to the power of 4 plus 3. Okay, let's substitute for u, put back in the x to the 5 plus 3x, so that goes over there, 1 over the square root of 1 minus that, times that object, and so dy dx is this expression here. Okay, there's the derivative, just using the chain rule and the rules above. Let's have a look at this one. The derivative of y equals sine of inverse tan x on 5. All right, here we go. So let u equals inverse tan x on 5, then y equals sine of u. Dy dx by the chain rule is dy du times du dx. Okay, think of it as the du's here cancelling, and we're left with dy dx. Okay, so dy du, what's the derivative of sine u? Well, it's cos u. What's the derivative of du dx? What's the derivative of u if it's inverse tan x on 5? Well, it's 5 over 5 squared plus x squared. Okay, putting this all back in, cos of u, let's put u back in, cos of inverse tan x on 5 times 5 over 5 squared plus x squared. Okay, another example there. One more example to go. I think this might be the last one. All right, now y equals inverse sine b times x on a. B and a take as constants. Let u equals bx on a. Then y equals inverse sine of u. Chain rule again, dy dx is dy du times du dx. Dy du is 1 on the square root of 1 minus u squared, because u over 1 is just u. Du dx is b on a. Okay, and what we're left with then, dy dx is b on a times the square root of 1 minus bx on a all squared. And that's it.